properly calculate voltage drop when a motor is involved, consider this example. The scenario involves determining the correct size of a THHN conductor for a 3-phase, 5 horsepower, 460 volts, design E induction motor. The motor has a power factor of 0.20 and the distance between the motor and the motor control center, or MCC, is 405 feet. The line voltage is 460 volts. Firstly, determine the motor's full load current, or FLC. For a 5 horsepower, 460 volts, 3-phase induction motor, which is design E, the FLC is approximately 8.8 amps. Because the power factor is 0.20, the apparent current is derived by dividing the FLC by the power factor. That is, apparent current equals FLC divided by the power factor, which equals 8.8 amps divided by 0.20, resulting in 44 amps. Secondly, determine the voltage drop, or VD. Use the lock rotor current, or LRC, method. Voltage drop equals LRC multiplied by the circuit impedance multiplied by the distance, and the result is divided by 1000. The locked rotor current typically ranges from 500% to 600% of the full load current. Assume 550%. Locked rotor current equals 550% multiplied by the full load current, which equals 550% multiplied by 8.8 amps, which is 48.4 amps. Circuit impedance can be approximated as circuit voltage divided by the apparent current multiplied by 1000. Circuit impedance equals 460 volts divided by 44 amps multiplied by 1000, which is 10.45 ohms. Plugging in the values, voltage drop equals 48.4 amps multiplied by 10.45 ohms multiplied by 405 feet, then divided by 1000, which is 20.6 volts. Thirdly, determine the required conductor size. Apply the 125% FLC rule for motor circuits. Adjusted FLC equals 125% multiplied by the FLC, which equals 125% multiplied by 8.8 amps, which equals 11 amps. Using the National Electrical Code, or NEC, Table 310.16, a THHN conductor with an ampacity of 15 amps is required for a voltage drop of 20.6 volts over a distance of 405 feet. Therefore, a 15 amp THHN conductor is required for this application. Here's a more detailed breakdown of the calculations and the NEC considerations involved. First, calculating the motor full load current, or FLC, is essential. NEC Table 430.250 provides FLC values for 3-phase alternating current motors. However, since the question specifies a design E motor and provides a power factor of 0.20, we use the given FLC of 8.8 amps. This low power factor significantly impacts the calculations, emphasizing the importance of using the correct motor characteristics. Next is the apparent current calculation. The apparent current is calculated as FLC divided by the power factor. This step accounts for the reactive power due to the low power factor. Using the formula, apparent current equals 8.8 amps divided by 0.20. The result is 44 amps. This higher apparent current is crucial for accurate voltage drop calculations and conductor sizing. For calculating the voltage drop, or VDE, the locked rotor current, or LRC, method is employed. The LRC is a multiple of the FLC and represents the current drawn by the motor startup. Typically, LRC ranges from 500% to 600% of the FLC. Assuming 550%, LRC equals 550% multiplied by 8.8 amps, which is 48.4 amps. This value is used to estimate the worst-case voltage drop during motor startup. The circuit impedance is approximated using the formula Z equals voltage divided by current. In this case, we use the line voltage and the apparent current to estimate the impedance. Circuit impedance equals 460 volts divided by 44 amps, which is 10.45 ohms. This impedance value is critical for determining the voltage drop over the given distance. Voltage drop equals LRC multiplied by the circuit impedance multiplied by the distance, then divided by 1000. Plugging in the values, voltage drop equals 48.4 amps multiplied by 10.45 ohms multiplied by 405 feet, then divided by 1000, which equals 20.6 volts. This voltage drop value is then used to determine if the selected conductor size is adequate. Determining the required conductor size involves several NEC considerations. NEC section 430.22 requires motor circuit conductors to have an ampacity of not less than 125% of the motor's full load current. Adjusted FLC equals 125% multiplied by 8.8 amps, which is 11 amps. This adjusted current is used to select the appropriate conductor size from NEC Table 310.16. NEC Table 310.16 provides ampacity ratings for various conductors based on insulation type and installation conditions. For THHN conductors, the table shows that a 14 American wire gauge, or AUG, conductor has an ampacity of 15 amps, which meets the 125% FLC requirement. However, voltage drop must also be considered. NEC recommendation is that voltage drop should not exceed 5% from the source to the farthest motor. In this case, the calculated voltage drop is 20.6 volts. To check if this is within the acceptable range, calculate the percentage voltage drop. Percentage voltage drop equals voltage drop divided by the source voltage, multiplied by 100. Percentage voltage drop equals 20.6 volts divided by 460 volts, multiplied by 100, which is 4.48%. Since 4.48% is less than 5%, the voltage drop is within the acceptable range. Therefore, based on the 125% FLC rule and the acceptable voltage drop, a 14 AWG THHN conductor with an ampacity of 15 amps is suitable for this application. This comprehensive calculation ensures that the selected conductor size meets both the ampacity requirements and the voltage drop limitations, providing a safe and efficient motor circuit. In summary, to calculate voltage drop from motor: 1. Determine the motor's full load current, or FLC, from the motor nameplate or NEC tables. 2. Calculate the apparent current using the power factor. 3. Determine the lot rotor current, or LRC, as a percentage of the FLC. 4. Approximate the circuit impedance using the line voltage and apparent current. 5. Calculate the voltage drop using the LRC, impedance, and distance. 6. Apply the 125% FLC rule to determine the minimum conductor ampacity. 7. Select the conductor size from NEC Table 310.16 based on the calculated ampacity and voltage drop requirements. Finally, verify that the voltage drop is within the acceptable limits, typically 5%. By following these steps, one can accurately determine the appropriate conductor size for a motor circuit, ensuring compliance with the NEC and safe, efficient operation. Consider how different factors affect the outcome. The motor's design type, whether it's design B, C, or E, influences the FLC and LRC. Design E motors, known for their high efficiency, often have low power factors affecting the apparent current and voltage drop calculations. The power factor, which is the ratio of real power to apparent power, affects the current drawn by the motor. A lower power factor results in a higher apparent current, increasing the voltage drop. The distance between the motor and the power source directly impacts the voltage drop. Longer distances result in higher voltage drops, requiring larger conductors to maintain voltage within acceptable limits. The conductor material, whether it's copper or aluminum, affects the conductor's resistance. Copper has lower resistance than aluminum, resulting in lower voltage drops for the same conductor size. The installation method, such as conduit type and ambient temperature, affects the conductor's ampacity rating. Higher ambient temperatures reduce the conductor's ampacity, requiring larger conductors to carry the same current. The NEC provides tables and guidelines for dating conductors based on installation conditions. The voltage drop limit, typically 5%, is critical for ensuring proper motor operation. Excessive voltage drop can cause reduced motor torque, overheating, and premature failure. Consider the implications of using a different locked rotor current percentage. If a locked rotor current of 600% is used instead of 550%, the voltage drop calculation changes. Using 600%, LRC equals 600% multiplied by 8.8 amps, which is 52.8 amps. Then, voltage drop equals 52.8 amps multiplied by 10.45 ohms multiplied by 405 feet, then divided by 1000, which is 22.3 volts. The percentage voltage drop equals 22.3 volts divided by 460 volts, multiplied by 100, which is 4.85%. Even with the higher LRC percentage, a voltage drop is still within the acceptable 5% limit. However, it's closer to the limit, indicating that a larger conductor size may be necessary for long-term reliability. Consider the impact of using a different conductor material. If aluminum conductors are used instead of copper, the resistance increases, affecting the voltage drop. Aluminum conductors have a higher resistance per foot compared to copper conductors of the same size. This increased resistance results in a higher voltage drop for the same current and distance. To compensate for the higher resistance, a larger aluminum conductor size is required to achieve the same voltage drop as a smaller copper conductor. The NEC provides tables for aluminum conductor ampacities and voltage drop calculations. Consider the effect of ambient temperature on conductor ampacity. If the ambient temperature is higher than the standard 30 degrees Celsius, the conductor's ampacity must be derated. The NEC provides derating factors for various conductor insulation types and ambient temperatures. For example, if the ambient temperature is 40 degrees Celsius and the conductor is THHN, the derating factor may be 0.91. This means the conductor's ampacity is reduced to 91% of its listed value. To ensure the conductor can carry the required current, a larger conductor size may be necessary. Always consult the NEC tables for specific derating factors and ampacity adjustments based on ambient temperature and installation conditions. Also, consider the impact of harmonic currents on conductor sizing. Nonlinear loads, such as variable frequency drives and electronic equipment, can generate harmonic currents that increase the overall current in the circuit. Harmonic currents can cause overheating and premature failure of conductors and equipment. To mitigate the effects of harmonic currents, it may be necessary to use oversized conductors or install harmonic filters. The NEC provides guidelines for sizing conductors in circuits with harmonic currents. Also, consider the impact of voltage drop on motor performance. Excessive voltage drop can cause reduced motor torque, lower efficiency, and increased operating temperature. These factors can shorten the motor's lifespan and increase energy consumption. To ensure optimal motor performance, it's important to maintain voltage drop within acceptable limits, typically 5%. If the voltage drop exceeds this limit, a larger conductor size or a higher voltage power supply may be necessary. Also, consider the benefits of using voltage drop calculation software. Several software programs are available to simplify voltage drop calculations and conductor sizing. These programs can account for various factors such as conductor material, installation method, ambient temperature, and harmonic currents. Using voltage drop calculation software can save time and reduce the risk of errors, ensuring that the selected conductor size is appropriate for the application. In summary, accurately calculating voltage drop for motor circuits involves considering several factors such as motor characteristics, conductor properties, installation conditions, and NEC requirements. By understanding these factors and following the appropriate calculation methods, one can ensure that the selected conductor size provides safe, reliable, and efficient motor operation.